When a massive corporation goes bankrupt, the ripple effects just tear across the entire global economy. But there is always this billion-dollar mystery lingering right at the center of the fallout. How much money do the bond investors actually get back? Predicting this, what we call the recovery rate, is honestly one of the most high-stakes, computationally complex challenges in modern finance. And for decades, the biggest computers and the most advanced classical AI models have completely struggled to get it right. But what if I told you the solution isn't some massive room-sized supercomputer, but something incredibly tiny? Welcome to our explainer for today. We're going to dive into some fascinating new research that proposes a true David versus Goliath story. We're looking at how a tiny quantum circuit, using literally just 8 qubits, is taking on massive, data-hungry classical AI models to predict these credit recovery rates. And spoiler alert, it's actually winning. So here is our roadmap for today. We'll start with 1, the billion-dollar guess. Then cover 2, why classical AI fails. 3, the quantum highlight. 4, angle versus amplitude encoding. 5, the promising results. And finally wrap up with 6, the quantum future. Okay, let's jump straight into section 1, the billion-dollar guess. Right now, in trading rooms all around the world, investors and risk managers often rely on this dangerously simple assumption. When they're pricing distressed bonds, they frequently just assume a constant recovery rate of 40%. Basically, they assume that if a company defaults, they'll magically get 40 cents back on the dollar across the board. But as you might guess, empirical data proves this is a massive oversimplification, and it leads to some terribly flawed pricing models. Because look at what the actual data tells us. The real recovery rates range anywhere from 0% to over 100%. And notice this bimodal distribution here. What that means is the outcomes heavily cluster around 2 extreme poles. Either you lose almost everything and get maybe 10% back, or you recover almost everything, right near 100%. So it's a wildly unpredictable guessing game. If you're relying on traditional averages like that 40% rule of thumb, you are for sure flying completely blind. Which brings us to section 2, why classical AI fails. To train an AI, you obviously need data. And the researchers we're looking at today compiled an absolutely incredible data set spanning from 1996 all the way to 2023. It includes 1,725 default observations across 576 firms. But here's the real kicker. Every single default is evaluated against 256 highly complex features. We're talking macroeconomic indicators, bond-specific traits, firm-level financials, risk sentiment, the whole shebang. The dimensionality of this data is just staggering. And this is exactly where classical machine learning chokes. Why? Well, first off, data sparsity. Thankfully, corporate defaults are pretty rare, which gives us a small sample size. But then we take that small sample and combine it with a massive, high-dimensional feature space, those 256 variables we just talked about. When classical models like feed-forward neural networks or XGBoost try to process this, they hit severe scaling issues and end up completely overfitting. Now, you might be thinking, hey, how is this different from data quantitation? Well, in classical machine learning, quantitation often just dumbs down the precision of the numbers to save space, which means you lose critical nuances. But without it, these classical models try to process everything at full resolution, and they essentially just cheat. They memorize the practice test, and then they completely fail the real exam when they see new data. Moving on to section 3, the quantum highlight. The researchers knew they desperately needed a way to process high-dimensional data without triggering that overfitting trap. So what is the highlight of their research? It's a technique called amplitude encoding. This is the critical magic trick that makes this whole solution possible. Amplitude encoding is a quantum machine learning technique that takes all that messy, complex classical data and encodes it directly into the amplitudes of a quantum state. The end result? You get exponential data compression, but, and this is key, it actually preserves those complex, nonlinear relationships instead of just dumbing them down. Let's break that down a bit more in section 4, angle versus amplitude encoding. So previously, researchers tried a different method called angle encoding. Think of angle encoding like driving to a destination where every single piece of your luggage needs its own separate car. It maps one data feature to exactly 1 qubit. For our financial data set, that means we need 256 perfect qubits, which is pretty much impossible on today's quantum hardware. But amplitude encoding? It's like inventing a hyperdimensional bus. Because it scales logarithmically instead of linearly, it compresses the data exponentially. Thanks to the math behind this amplitude encoding, the researchers were able to compress all 256 complex financial features into just 8 qubits. Yep, just 8. That is an absolutely monumental reduction in processing overhead. Which brings us to the big question in Section 5, the promising results. Exactly how promising are these results? Well, take a look at the root mean squared error here. This basically measures how wrong the predictions were. The classical feed-forward neural network scored a 0.246. The older quantum angle encoding method scored a 0.242. But our tiny 8-qubit quantum amplitude encoding model, it achieved the lowest error rate of all, 0.228. It didn't just compete with the Goliath models, it won the prediction battle with a statistically significant lead, proving to be way more accurate and much more stable. But why did it win? The researchers point to this really fascinating concept in physics. They note, the intrinsic unitarity of quantum circuits naturally constrains model capacity and helps reduce the risk of overfitting. Okay, in plain English, unitarity essentially means that quantum operations have to preserve the total probability of the system. This acts as a natural, built-in guardrail. It physically prevents the AI from wildly distorting the data just so it can memorize the training set. It essentially forces the model to actually learn the broad general patterns of the financial market. Finally, let's look at Section 6, the quantum future. Okay, we do have to ground the hype for just a second here. As incredible as these results are, there are still some real hurdles. The researchers conducted these tests on fault-tolerant quantum simulators, not physical quantum computers. We are currently in what's known as the NISQ era, noisy intermediate scale quantum. Real quantum hardware today is still very prone to noise and decoherence. And because amplitude encoding requires pretty deep, complex circuits just to prepare the initial state, a real-world quantum computer today might introduce too many errors. So we're essentially waiting on advances in quantum error correction before this can be deployed directly on Wall Street. But the proof of concept is undeniably here, and honestly, it leaves us with a massive question. If an algorithm running on just 8 simulated qubits can beat our most advanced classical neural networks today, what on earth is going to happen to global finance when real, physical quantum hardware scales up tomorrow? We're standing right on the edge of a computing revolution that is going to completely rewrite how risk, money, and data are understood. Thanks so much for joining me on this explainer, and I really hope you're as excited about our quantum future as I am.